Complex networks as big data. Very often when we work with big data, it shows up as a network. We need models that have multiple scales. We look at complex systems. They have a complex hygienous underlying structure, a topology, for example. Many of our applications are multi-scale. Chaos tends to be multi-scale rather than random. And emergence, which is often the motivation for what we're doing, is very often related to scale. Many of the questions associated with the big data are about relationships of one scale to another. But how do we model multiple scales? Well, graphs can model multiple scales. So for instance, here I have a triangle graph, and I add more vertices and more triangles, more vertices and more triangles, and I just keep doing this, and what I end up with is a fractal called a Sierpinski triangle, and it has features at all scales. If we zoom, we would actually get the same graph. So that means big data often occurs as a complex network. Networks can encode the underlying structure of a complex system. For example, social networks, like a Facebook network, where an edge between two people would exist if they are friends. Maybe you want to study this so you can predict other people that might want to be friends. Social media, maybe you want to increase connections to your social media site. And here's an application of big data as a complex network. It's called Collusion, although it's now been renamed Lightbeam. And it's actually a Firefox add-on which allows you to see how your connectivity is growing. And to illustrate, I'm going to go to the ETSU homepage. And once there, I click on this collusion graph and we see that there are two vertices. But then I'm going to go to the bookstore. Let's see what's happened with the collusion graph, which is now again called Lightbeam. The bookstore, and you can see we're creating a network just by our searching patterns. And as we click, maybe we go to Amazon, and we see that the network becomes even more sophisticated. So we think we've gone to 3 different links, but in reality, we've gone to many different links, and just 5 minutes later, with just a little bit of clicking, we've got lots and lots of vertices in our collusion network, even though I've only clicked on 7 or 8 different vertices. So what's going on? Well, when I click on a page, that page is clicking on other pages who are clicking on other pages, and we're getting a very sophisticated network. It's interesting to note that the vertex that I actually started with is not the central one in my network in some sense. It's actually just this degree 4 vertex way over here on the side. So power grids, edges or wires. Often we want to study reliability. So what do all these networks have in common? Well, they're connected. So from any vertex, there's a path to any other vertex. In contrast, the subeconomy graphs we looked at earlier, they are not connected. They have multiple components. They represent real-world phenomena in flux, and that's these real-world networks that we've been looking at. So in these networks, nodes and edges are continuously added or removed, and the most connected nodes tend to become more connected. So real-world networks tend to grow. How? By adding vertices and edges. Disconnected graphs tend to become connected, and edges tend to be added faster than vertices. In many models, as a matter of fact, we'll often assume the edges are being added so fast that the vertices are not being added at all. We'll only assume the addition of edges. Now the set of all vertices in a graph connected to a vertex V is called the neighborhood of V, denoted like this, n sub g of V. The degree of V, denoted d of V, is the size of the neighborhood, or a better word would be cardinality, the number of elements in the neighborhood. In real-world networks, the larger the degree of a vertex, the faster it tends to add neighbors. We call this the rich get richer phenomena. And this leads to a concept known as scale-free networks and power law distribution of degrees. Now, what we mean by this is that if you look at the degree distribution for real-world networks, there tend to be many vertices that have lower degrees. Lots of vertices with degree 1, degree 2, degree 3. And there tend to be relatively few that are very high degree. Now, if we look at this as a histogram, in other words, if we relate the count to the number, d, which is the degree, then we tend to get a power law. So a power law is just where we have a constant times d, which is our independent variable here, the degree, to the negative p for some constant p. The count here is actually a function, count of d. It's the number of vertices with degree d. So when we say power law, we mean that count d as a function of d is proportional to d to the negative p for some constant p. And a graph is scale-free if its degree distribution follows a power law, at least asymptotically. Now, let's see what this looks like. If we have the count as a function of d, that's the number of vertices with degree d, then we can plot this as a bar chart. The count on the vertical axis, counts on the vertical axis, and the degrees on the horizontal. And we'll see that these bars have this power law distribution. And if we replace the bars by points, then we can better see this kd to the negative p function of count of d as a function of d. Notice that if we take the logarithm on both sides, we get the logarithm of the count of d is equal to the logarithm of k minus p times the logarithm of d. So what we actually have here is that the log-log plot of a power law is a straight line. So if we actually change the way the vertices are labeled, notice that now we have marked off in this unit a 1, the same distance on the x-axis as a 10, then 100, then 1,000, and so on. Here 100, 1,000, 10,000. So we've marked things off as powers of 10. And when we do that, this is called a log-log plot, and a power law is a straight line in a log-log plot. So there you see the straight line. So let's do something. Let's take the total count to be the sum of all these possible counts. And then if we define P of D to be the count of D over the total count, then P of D becomes a relative frequency. And that means the highest possible we could get is 1. And so now we have a rescaling of the axis from 0 to 1. Notice it's still a log scale. And then P of D is the approximate probability that a vertex V chosen at random will have degree D. For some more examples of scale-free networks, let's look, for instance, at the airline networks. So the larger the node, the greater the number of daily flights. And so we have all of these different nodes or airports, and they're all connected. And notice we have a log-log plot, and we have the probability relative frequency here, and it looks very much like a power law distribution, a straight line in a log-log plot. Now, when we say scale-free, we said asymptotic earlier, and that means scale-free means eventually power law. There's several reasons for that. First off, low degree vertices you don't want to really think of those as part of the power law distribution. And the reason for that is that very large numbers of lower order vertices means that you may have a hard time counting them accurately. And in general, you'll tend to undercount because they're also hard to detect. If there are lots of isolated degree 1 and degree 2 and even degree 0 vertices, those will be hard to record. So in a social network, if you're not hooked up to anybody, it'll be hard to know that you're there, for example. So power law often emerges only after reaching relatively high degree vertices. Let's look at an example. So I'm going to load network X, and then I'm going to look at this Facebook network that I used in the My Favorite Die to model the groups going to lunch. They were friends in a Facebook network, and it was this network that they were friends in. This is a very small network, just 4,000 vertices or so. There's its degree distribution. And now I'm going to plot this using a bar graph. And you'll see that it's going to look very much like a power law distribution. But it's a social network, and that tends to mean that we undercount the number of low degree vertices. So you can see we don't have good measures below 10, but it looks like a straight line in a log-log plot once you get far enough out. So we see this often in the life sciences. So here's a metabolic networks where the vertices are chemicals and the edges are biochemical reactions. And gene regulatory networks where the vertices are genes and the edges are causal links. So here we have metabolic networks, log-log plots, and all three domains, archaea, bacteria, and eukaryotes. And you can see it looks roughly like power law distributions. Gene regulatory networks, we've got the red dotted lines there to kind of show you that you eventually become close to a power law distribution. However, not all networks are scale free, so highway systems tend to be exponential. So most vertices in an exponential network have about the same degree, the expected value bracket k. Another example are yeast protein networks. The vertices are proteins and the links are bindings between those proteins. And in this paper they showed that the best fit was actually somewhere between scale-free and exponential. So a yeast protein network is not quite either one. So scale-free is somewhat of a goal. Real-world networks are often scale-free. Theoretical graphs, however, often are not. Our subeconomy graph was not scale-free, for example. Now, sometimes we can improve our models by pushing them towards scale-free, but not all real-world networks are scale-free. Geometric or physical constraints can limit the rich get richer paradigm. For example, one of the reasons that highway networks are not scale-free is they tend to be planar. We don't tend to have lots of edges crossing each other for obvious reasons.